When gravity is the only force acting on the basketball, its mechanical energy is conserved regardless whether the ball is going up or down. The presence of air resistance, however, inhibits the ball from reaching the maximum height when thrown upward, or reaching maximum speed when falling down. Friction force does dissipate mechanical energy. That's where we stopped in the last video. But what distinguishes friction force from gravitational force? Well, the difference comes in the form of this so-called conservative force versus dissipative force. Gravitational force is a conservative force in the sense that it conserves mechanical energy. A more formal definition of conservative force is related to the work done by such force. A force is conservative if the work done by it is independent of the path taken, i.e., it depends only on the starting and ending points. If this does not make any sense to you, consider this illustration. A man jogs from point A to point B. There are a number of roads from point A to B, going through the less beaten village track, or by the Mandarin Valley, or straight along the expressway. Nonetheless, as depicted here, point B is higher than point A. If we set point A as the ground, then point B is its vertical distance away above the ground. If we are then to compute the work done by gravity from point A to B, it will be given by negative mgh. Notice that the man does move along horizontal as well as vertical direction, but as far as gravity is concerned, only the vertical displacement is concerned because gravity acts vertically. By the same argument, the work done by gravity along other paths, the hilly and Mandarin Valley Trail, are also the same. At the end of the day, it doesn't matter if the man goes up and down the hill or runs around to get from point A to point B. The vertical displacement of the man between the initial point A and the final point B is the same for all three paths. Since work done by gravity is determined only by this vertical displacement, the work is the same for all three paths. That's what we mean by the work done is independent of the path taken. Gravitational force is thus a conservative force by definition. The fact that work done by conservative force is independent of the path taken implies that if the initial and final point are the same, like in the case when the man runs in a loop, the work done will be zero. There is no displacement if the path forms a loop, and hence there will not be any work done. It takes negative work done by gravitational force for the man to go up from point A to B. It will then take positive work done by gravitational force for the man to go down from point B to point A. In other words, the work done is reversible. In contrast, friction always opposes the motion. You push the box to the right, friction is acting to the left, and hence it will do negative work on the box. But if you reverse the motion and pull the box back to the left, friction is now acting to the right, and it will still do negative work on the box. The work done by friction in the second phase does not become positive. Work done by friction is not reversible. Hence, although the initial and final position of the box are the same, work done by friction is not zero. Friction force is thus not conservative. It is dissipative, as it causes mechanical energy to dissipate. Consider this situation. A box is sliding unhindered on an icy slippery surface at speed vi until it encounters a rough gravel surface. The friction causes the box to stop eventually after the box covers a distance delta d. We can compute the work done by friction in terms of the initial speed of the box, in the same manner when we were deriving work energy theorem. If you recall, 1/2 mv square is the equation of kinetic energy. This was the kinetic energy of the box just before it hits the gravel surface. So what do we learn from this calculation? Well, yes, friction dissipates mechanical energy. In this context, the mechanical energy comes solely from the kinetic energy. But the dissipated kinetic energy does not simply disappear. Instead, it is converted into other forms of energy, such as heat or sound, which are byproducts of the work done by friction. If we are able to somehow account for all the dissipated energy, that is to say, we are able to measure the amount of heat and sound generated, we will find out that this amount will be equal to the change in the kinetic energy of the box. In conclusion, we can then say that the work done by friction force is equal to the negative change in the mechanical energy of the box. The kinetic energy of the box will decrease while heat is generated. Indeed, in general, work done by dissipative force implies negative change in the mechanical energy of the system. Well, you guys know where we are going from here. We have gone through something similar when deriving the conservation law of mechanical energy in the last lecture video. What we do next is to bring all the terms to one side and define a new notion, universal energy. It is universal in the sense that it encompasses the mechanical energy of the system, its potential and kinetic energy, as well as the dissipated energy that goes to the environment in the form of heat, sound, etc. In that sense, the change in the total energy in the universe is zero, which means that the total energy of the universe is conserved. It does not change. So we have from previous lecture the conservation law of mechanical energy. Do you remember its assumption? The conservation law of mechanical energy is valid in the absence of dissipative forces. In this lecture, we learn the conservation law of universal energy. You may think of mechanical energy as a subset of universal energy, as the latter takes into account the former plus the amount of energy we dissipate to the environment. In that sense, universal energy takes into account everything. When you were first exposed to the notion of energy in primary or lower secondary school, you might recall your teacher or your text mentioned something along energy could be converted, but it is neither created nor destroyed. I remember my primary teacher did say so. That is the conservation law of universal energy. If you think about it, conservation of mechanical energy is not something very realistic in nature. It is not something you would normally encounter on day-to-day basis. A simple phenomenon, say a ball being dropped. You would likely to see the ball behave as shown. If we are to plot its trajectory, it can easily be seen that every time the ball hits the ground, certain fraction of mechanical energy is converted into heat, sound, and even the deformation of the ball requires energy. As a result, the kinetic energy and potential energy of the ball keeps decreasing as indicated by the decreasing maximum height. It will eventually come to a halt as expected.